All right, folks, let's hop into our time machine and travel back. Way back. We're talking 2,000 years ago when the biggest mystery wasn't the Wi-Fi password, but space itself. Back then, people looked up and thought, what is this vast, twinkling expanse? They didn't have fancy telescopes or satellite images. No, they had something better: imagination and curiosity. For Aristotle, space was kind of like water to fish. It's everywhere, it's necessary, but what is it? He believed everything existed in space, but space itself, it didn't have its own characteristics. Imagine thinking about the air around you. You know it's there, but can you see it? Can you touch it? And the idea of empty space. To him, that was like trying to imagine a cake with no sweetness. Just didn't compute. Fast forward to today, the description switched from myths and legends to mathematical terminology. The leader of this revolution was Newton. Galileo's 1632 publication of his work asserting that the Earth revolved around the Sun drew criticism from the Roman Catholic Church. The foundation of relativity was laid by Galileo's claim that every uniform motion is relative to any other constant motion. He was once found to be a heretic, and the Church bound his work until 1835. Later, Newton asserted that time and space would exist in a cosmos devoid of matter to experience motion. He eventually described space as a universal absolute, a complex statement on which motion was acted out. The absolute, accurate, and mathematical time flows evenly, without regard to anything outside itself and from its essence. Stephen Hawking once said, "You may watch a cup of tea fall from a table and smash into bits on the floor, but you will never see the cup gather itself together and leap back on the table." Ancient Greek intellectuals were preoccupied with time, just like space. While Hindu thinkers understood time as cyclical, from creation to destruction over 4 billion years, Aristotle claimed that time is simply the distance between before and after. Yet the exact origin of time has since become obscure. Time moves in one direction with a clear past and an impending future. Before thinking about time, we must consider horses and steam engines. Before the Industrial Revolution, using horses and cows as laborers was straightforward, because a fixed number of hay bales could ensure an animal's ability to work for a full day. Yet the question was raised: since feeding an engine horse would cost more than using it, how much work could be done with a pile of coal in a steam engine? Thermodynamics was then born as a result of it. The engine was now barely operating at 3% capacity. Although some fires in a physical steam engine emit heat into the air, others are utilized to boil water. Metal rubbing on metal causes a definite loss of energy that is unavoidable in every steam engine. It screeches loudly and is hot to the touch. As a result, the idea of entropy was developed to explain this rise in default and chaos. This is true for steam engines and planets, which will eventually degenerate into stars and galaxies. Although mechanical energy is unbeatable, there is a universal tendency for it to dissipate, which results in the exhaustion of potential energy across the material universe. Lord Kelvin first put forth this theory, after whom the measurement unit was named. If the cosmos were finite and left to obey the laws of nature, the inevitable outcome would be a condition of universal repose and death. James Clerk Maxwell, the famous Scottish physicist of the 19th century, was another great mind preoccupied with entropy and the arrow of time. With the help of a demon, his thermodynamics theories helped define how we think about heat and gases. He knew that if he combined two gases, a hot gas and a cold gas, they would become warm gas. He used the demon to change it from a state of disorder, the heated gas, to one of order. The two gases in a divided form of the hot gas aside and the cold gas aside. The Landauer limit is the unavoidable energy leak that results from deleting even a single piece of data. One of the critical components in constructing a time arrow is forgetting knowledge. Although fundamental physics still lacks a conclusive explanation, it is an intriguing option. Light speed has always been a mystery. It was demonstrated by experiments carried out years ago that it moved more quickly than sound. Ole Romer, a Danish astronomer, discovered the solution in 1676 while viewing Jupiter's moons as they circled the giant planet. According to Christian Huygens' calculation, the light must travel more than 211,000 kilometers per second, which is close to our current estimate of 300,000. Romer's finding is renowned for uniting electricity and magnetism into a single concept, electromagnetism, and for confirming that light was swift and finite. The only source of light he discovered was a combination of the two. but it still needed to be clarified to what this speed was in relation. Then Einstein entered the scene and questioned why magnetism and electricity did not conform to Galileo's relativity. After learning about special relativity in 1905, Hermann Minkowski, Einstein's former professor, investigated the geometry of these new equations in 1908. He made the observation that it was simpler to combine space and time into spacetime. Moreover, Minkowski's space was created by geometrizing spacetime from one observer to another. Once he passed away, Einstein decided to devote his attention to contemplating gravity. He concluded that gravity might control the relative ticking of a clock, but that gravity itself was not a force. Carl Schwarzschild solved the field equations of relativity for a spherical mass in 1916. He learned that a Blackmore bends time and space. Moreover, large gravitational pulls are produced by severe curvature. Nothing can escape, not even light. His idea was validated by studies of the deflection of starlight in 1919, making Einstein a household name in science. One of the strangest experiments to support Einstein's theory was Richard Keating and Joseph Haffel spending $7,600 in 1971 to fly 2 planes around the globe. The clocks were in sync, but when they returned, they were off by a few hundred nanoseconds. Taylor and Hulse concluded that Einstein's gravitational waves were the perfect culprit later in 1993. They dug into general relativity mathematics and calculated how the orbiting stars created ripples in spacetime, demonstrating how they could take away just the right amount of energy to explain the orbital demise. For their finding, they were awarded the Nobel Prize. The Laser Interferometer Gravitational Wave Observatory, or simply LIGO, was the experiment. The conclusion reached was that the universe continues to grow over time. Later, Steve Weinberg disputed that space does not expand since it is nothing. The passage of time varies depending on where you are. The knowledge of the past, present, and future is already present in each particle, continually moving. As people are composed of worldly particles, when a person dies, the particles scatter throughout the infinite universe. The universe began 16 billion years ago, but the precise mechanism has not, to this date, been identified. Sir Roger Penrose, the recipient of the Nobel Prize, considered the initial entropy and concluded that the likelihood of this happening by accident is 1 part in 10 to 10 to 123. What do you think about space and time? Feel free to share your views in the comment section below. Thank you for watching this video, and don't forget to subscribe to our channel so that you can always get a notification when we post the latest and most exciting space news that you would not want to miss. Till next time. Cheers!